Welcome to another physics video. Today we talk about deriving the four kinematic equations for constant acceleration. If you have not watched the video on constant acceleration, please watch that before watching this one. In the video on constant acceleration, we did derive the four kinematic equations, but it was kind of mixed with teaching constant acceleration as well. And it's so important to learn how to derive equations and expressions by yourself that I really want to touch on this topic a little bit more. For instance, imagine that you're getting ready to take your test. You've been studying really hard, and one of the problems on the test is asking for the final position of some object under constant acceleration, and darn it, you forgot the formula. You forgot the expression. You forgot it. So what are you going to do? How are you going to figure it out? So understanding how the four equations came to be and understanding where they come from, guess what? If you did forget on your test, you can now duplicate it, and it's extremely simple. So let's go ahead and get started. In the constant acceleration video, it stated that the instantaneous acceleration is equal to the average acceleration, and that's because the acceleration is constant. So since this is true, we can use the average acceleration, which is the one without the limit sign. We could use this to derive some interesting expressions, some powerful expressions for objects under constant acceleration in, I should say, one dimension. Alright? So what is the average acceleration? Well, acceleration is equal to the change in velocity over the change in time. And that's the average acceleration. Alright? So what deriving the four kinematic equations is all about is basically algebra gymnastics. You're looking at your expression and you're trying to find other ways you can write it. So there's a couple things here already. The change in velocity, that can be rewritten because we know change in velocity is nothing more than its final velocity minus its initial velocity. And change in time is nothing more than its final time minus its initial time, which for this video we will just call t, since the initial time will be 0. Alright, so imagine that you see a problem and it's asking you for the final velocity of an object under constant acceleration, and it gives you the acceleration, it gives you the initial velocity, and it gives you the time. Well, it might be a little easier to use a formula that's solved already for the final velocity. So all you have to do is plug in your information. So where does that come from? Well, you substitute, you do your algebra gymnastics, and you substitute these equal expressions in for your original. So you get acceleration is equal to final velocity minus initial velocity over t, time. Alright? Now, if a problem is asking you for your final velocity, well, let's go ahead and solve for it. Let's see if we can get an expression that is in terms that is geared at solving for the final velocity. So, you multiply each side by time, right? This is just simple algebra. Alright? So this leaves you with final velocity minus initial velocity is equal to the acceleration times the time, and we want to solve for final velocity. So we add initial velocity to each side, and the final velocity is equal to the initial velocity plus the acceleration times time. Keep in mind, super important, keep in mind that this is for constant acceleration only. This does not apply if the acceleration is not constant. Alright, because then you'd still have the limit sign in front of everything and it'd be a huge mess. This is only for constant acceleration. But if you look in your physics textbook or anywhere else, you'll see that usually this is the first powerful kinematic equation for constant acceleration. Alright, so you finished that problem. You found your final velocity and everything. You're on to your next problem on your test, and suddenly it's asking you about the final position of an object, knowing the initial position and knowing the average velocity and knowing the time, and it asks you for the final position, and you're like, darn it, I don't remember that formula. I don't remember that expression. Well, there is a very easy way of deriving another kinematic equation, and that's realizing since constant acceleration varies linearly in time, meaning it's constant, the average velocity is actually going to be equal to the initial velocity plus the final velocity divided by 2. It simply will be the arithmetic means. Alright? And we also know that average velocity is equal to your change in x over your change in time, your displacement over time, which we know to be your final position minus your initial position over t. Alright? So, combine. Now, if we were trying to make an expression for final position, then we should probably combine these two ideas here and solve for our final position. So, plugging this in for our average velocity, we get the initial velocity plus the final velocity over 2 is equal to the final position minus the initial position over t. Now it's simply, once again, algebra gymnastics. Multiply each side by t, and you get 1/2 of the initial velocity plus the final velocity times the time, right? Equals the final position minus the initial position. Now, if we add the initial position to each side, we actually solve for the final position, which is the initial position plus 1/2 of the initial velocity plus the final velocity times the time. So here is the second main kinematic equation for constant acceleration, and once again it was derived from very simple expressions. Do not try to memorize these. Practice deriving these. Alright, so you finished that last problem. You're moving on to the next one. It's asking you for the final position of another object. This time, though, it doesn't give you the final velocity, which you notice in your second kinematic equation here, that's kind of a requirement for this particular equation. So, and on top of that, you forgot the third kinematic equation. So what do? Well, you basically do some more algebraic gymnastics. For your final velocity here, you could actually plug in your first kinematic equation right into where it has the v there. Let's go ahead and do that and see if we can get something without final velocity. Because notice, if we plug in this first expression, we no longer will have a final velocity in our second kinematic equation, which is the goal. So our final position is equal to our initial position plus 1/2 of the initial velocity plus the initial velocity plus at, because we just substituted this in instead of our final velocity, right? And all of that times t. Simplifying, we get final position is equal to the initial position plus 1/2 of the initial velocity times time plus 1/2 of the initial velocity times time plus 1/2 of the acceleration times time squared. Now we combine like terms, which are these two. We get the final position is equal to the initial position plus the initial velocity times time plus 1/2 of the acceleration times time squared. So it took me less than probably 1 minute to derive that one. Yet it's powerful. It gives you a relationship for the final position that doesn't even include its final velocity. So you now have another tool in your tool belt to solve constant acceleration problems, and you don't even have to remember the tool. You just have to remember how to do some algebra gymnastics. Alright, and the fourth kinematic equation is a little bit more difficult than the other two that we have derived, in the sense that it requires a little bit more algebra. But basically, for this one, the idea is we want to get a an equation for the final velocity, but one that does not have time within it. So what we're going to do is we're going to use equation 1, and we're going to solve for time, plug it into equation 2, solve for final velocity. So let's begin. And final velocity is equal to the initial velocity plus acceleration times time. So we're going to solve for t here. Acceleration times time is equal to the final velocity minus the initial velocity. Time is equal to the final velocity minus the initial velocity over acceleration. All I did there was divided each side by a. So this is what we're going to use to plug into the second kinematic equation in order to get rid of the time variable within our expression. So we have the final position is equal to the initial position plus 1/2 of the initial velocity plus the final velocity times time, which is the final velocity minus the initial velocity over acceleration. So simplifying this, we have the final position is equal to the initial position plus, now if you multiply these together, you're actually going to get v final position squared minus initial position squared. And go ahead and verify that using the distributive property. But I'm going to run out of space if I do it here. And then all of that is over 2a. Alright. Now from here, remember, we're looking for an equation for velocity, final velocity, that doesn't have time within it. And if you look here, there is no time symbol in it. All that's left to do is to solve for the final velocity. First, subtract your initial position from each side, which gets rid of this one here, and multiply both sides by 2a. But I'll go ahead and do it one step at a time here. So I'm going to move this to the left hand side. V squared final position squared minus initial position squared over 2a is equal to the final position minus the initial position. Alright, now for this next part, we're going to multiply each side by 2a in order to cancel this denominator here. This gives us v squared final position squared minus initial position squared equals 2 times acceleration times the quantity of the displacement, basically just the displacement. And alright, so all we have to do from here is add the initial velocity to each side, and we get the final velocity squared is equal to the initial velocity squared plus 2a times the final position minus the initial position. Alright, and this is the fourth kinematic equation. Here is the list of the 4 kinematic equations you can use for constant acceleration. These are only for constant acceleration. Thanks for watching the video, and if you have a test coming up with a timed test, make sure that you do try to memorize these to some extent, but your first priority should always be to master the derivation for it instead of just memorizing the formula without knowing the derivation.